organic chemistry and the different groupings that we can find based on their structure, what allows us to name them. We've already done hydrocarbons, things that have hydrogen and carbon only. In the hydrocarbons, we had two groupings. The alphatics, the ones that were basically straight, and the aromatics, the ones that contained benzene. The alphatics were alkanes that ended in -ane and meant all the bonds were single bonds. The alkenes ended in -ene and we had at least one double bond, and alkynes end in -ine, and in an alkyne we have a triple bond. We've also done a lesson on the first of our derivatives, and in the derivatives what we do is we add another element. We started with the alkyl halides, also called halocarbons. In these cases, we've added a halogen, and we've treated it like a branch. And we've added that branch onto my alkanes, alkenes, alkynes, or onto my aromatics. There are many other groupings of derivatives that allow us to have different name endings and different categories for naming. We're only going to follow 3 of them, although we'll talk about what some of the other ones are in a later lesson. In this video, I want to talk specifically about the group called the alcohols and the grouping called carboxylic acids or carboxyl acids. Alcohols are groups that contain an OH grouping as the functional group. Carboxylic acids are ones that on the end carbon you will have a double bonded O and an OH as a functional group. Remember that your functional group is that part of the molecule that changes the parent name. Alcohols change the parent name to end in -ol. Just like the double bond in the alkene changed the parent name to end in -ene. Carboxylic acids change the parent name to end in -oic acid. Let's take a look at these groups separately and give you some examples. So alcohols are any compound, organic compound, where we see an OH, a hydroxyl group, branching off in place of one of the carbon hydrogens. You'll notice that the hydrogen on this ethene molecule, so this was originally ethane. So we had originally ethane of 2 carbons with 6 hydrogens. This was ethane. What we've done is taken off one of the hydrogens, so we have a bonding site, and replaced it with an OH. Sometimes I'll write them backwards depending on how my spacing goes. The oxygen is the part bonded to the carbon because oxygen is capable of making 2 bonds, whereas hydrogen is only capable of making 1. When we've substituted this functional group, what we do is we get rid of the E and we change it to L. This is ethanol. And just like with a double or triple bond, we need to say where it exists on the molecule. In this case, it exists on carbon 1. Although in all fairness, whichever carbon you would put on would become carbon 1. Alcohols are classified as primary, secondary, or tertiary, depending on how many other carbons are attached to the carbon holding the functional group. In the top example, the carbon holding onto the hydroxide is attached to only one other carbon. Remember that R just means the rest of the chain. It could be a 1 carbon chain beyond that point, a 2 or a 300. R just means the rest of it. In the secondary alcohol below, the carbon holding onto the hydroxide group is attached to 2 other alcohols. It's attached to 1 on either side. In the bottom example, the carbon holding on to the hydroxide group is attached to carbons on 3 sides. We'll do examples of whether alcohols are primary, secondary, or tertiary. Now remember, when we name an alcohol, we're going to have to include the carbon that's holding onto the functional group. I can't actually highlight through my OH the same way I did with a double or triple bond because the OH is sticking off the chain. So what I do instead is make sure that I include the carbon holding onto the hydroxide. That carbon holding onto the hydroxide must be included in your parent chain. It also has to be given the lowest possible numbering so that the functional group gets the lowest numbering. We change the name to all. If there are 2 hydroxide groups, it's a diol. 3 would be a triol, etc. Take a look at this first example, ethanol. In ethanol, the carbon holding onto the functional group is this carbon. It is a 2-carbon chain. So by itself it would have been ethane, but because there is an OH at the end, it's ethanol. So ethanol is the kind of alcohol that is considered to be drinking alcohol. It is the only alcohol that is not poisonous in small amounts, although it is in large amounts. To the right, we have another 2-carbon chain. Both of these carbons are holding hydroxide groups, so they must both be included in the parent chain. So this again was an ethane molecule, but now there are 2 alcohol groups. Ethane, because it was based on a 2-carbon chain. Di, because there's 2 functional groups. All, because they're both alcohols. It is important that we say where those functional groups live. One of them's on carbon 1 and one of them's on carbon 2. Remember, it would have been possible to have made ethane diol with OHs both on carbon 1. This would also be possible. So we have to remember to make sure we include the numbering wherever possible, because if there's even one other possibility and you don't include your numbering, it would be considered incorrect. On the bottom left, a 1-carbon chain holding the functional group hydroxide is methanol. A 3-carbon chain, remembering that this carbon has to be included because it's holding the hydroxide, is a propanol. In this particular case, the carbon holding the hydroxide is on number 2. This is 2-propanol, also known as isopropyl alcohol. What do we do when the alcohol group is attached to a benzene ring? When the alcohol group is attached to a benzene ring, I know you very much want to call it benzenol. Unfortunately, benzenol already exists as a different molecule. So we now need to name it phenol. Phen, like the phenyl branch, but this time we'll pronounce it phe. And then OL means it's an alcohol. We pronounce this phenol to distinguish it from phenyl, pronounced phen, O, when we have a branch. In this case, the OL means we have an alcohol. Wherever possible, when we have a hydroxide group on a benzene ring, we refer to it as a phenol. So here is phenol. By definition, the carbon holding the hydroxide gets the lowest numbering. So the phenol is always on carbon 1. That makes the methyl branch the next lowest possible number. It is 2. This is 2-methylphenol. On the next example, again, this is phenol with the carbon holding the hydroxide getting the lowest number. The methyl gets the next lowest number, which is 3, 3-methylphenol. And in the last example, 4-methylphenol. Because there are only 2 branches, we could also use the ortho, meta, and para. We could call it orthomethylphenol, meta-methylphenol, or para-methylphenol. Methylphenol itself has a common name called cresol, which sounds like creosote, which you might hear about in the chimney, or that black shiny stuff that you see on the leftover piece of a burnt log. It's a methylphenol combination of ortho, meta, and para cresols. And being alcohols, they're quite flammable. So for benzene rings, find the phenol portion, call that your parent chain, and then label the branches as they come off. Now alcohols the small ones anyway, are at least partially soluble in water. This is because the OH molecule at the end gives them a somewhat polar nature. Longer than 4 carbons, however, the very large amount of nonpolar bonding in the carbon-hydrogen bonds makes them insoluble. So the bigger the alcohol, the less likely you'll be able to dissolve in water. Alcohols have higher boiling points than alkanes with the same number of carbons, but they still boil at relatively low temperatures and they are easy to turn into a gas. Alcohols are used in disinfectants, they're used as the basis for cosmetics and perfumes, they're used in antifreezes, industrial chemicals, and are very, very useful. Our next group that we're going to look at is the carboxylic acids. Carboxylic acids happen when the end carbon, and it's always the very end carbon, it will be carbon number 1, is double bonded to an oxygen on one side and single bonded to a hydroxide on the other. The double bond to the oxygen is called a carbonyl group, and the OH group is called a hydroxyl group. So this combination, which uses up 3 of the 4 bonds, and therefore requires that carbon always must be number 1, is my carboxylic acid functional group. Carboxylic acids always end in oic acid. So we find the carbon that contains the functional group, and again, it must be in the parent chain. Find the longest chain we can, including that carbon. In this case, there's 2. So 2-carbon chain would typically be ethane. But again, because we have this functional group, we drop the E and change it to oic acid. This is ethanoic acid. This is always carbon 1, the one holding the functional group, and we number away from it. Because carboxylic acids are always on carbon 1, we typically don't put a paired chain name for them. Suppose I had a carbon chain that had 4 carbons with the carboxylic acid functional group, and we have a branch. Again, when I go to name this, I find the carbon holding the functional group, find the longest chain I can, including that carbon. Anybody branching off of that becomes a branch. A 4-carbon chain would have been butane. But because we have the functional group, I'm going to get rid of the E on butane and change it to oic acid. This is butanoic acid. On my butanoic acid is a methyl grouping. Because this is carbon 1, and we have to call this 2, 3, 4, on carbon, not 4, on carbon 3, we will have my methyl branch. Looping this together, because again, organic names are all one big word, 3-methyl butanoic acid. How do I draw different compounds that include a functional group? Let's do a couple of examples. Whenever we have to draw organic molecules, we follow the following 4 steps. 1, draw the parent chain. 2, insert the functional group. 3, add any branches. 4, add hydrogens as needed in the direction and at the placements that are indicated. Let's take a look at the first example. Working my way from the back, I see that I have an oic acid. Oic acids mean that on some carbon, I'm going to have this OOH functional group. Trope tells me that my chain will be 3 carbons long. So my parent chain, step 1, will be a 3-carbon chain. 1, 2, 3. My functional group, which has to go on carbon 1 for carboxylic acids, is a double bonded O and an OH. Step 3 is to add any branches. There are 2 different branches here. Di means that we're going to have 2, and methyl means there are 1-carbon branches. 2 and 2 tells us where to put them. So if this first one is carbon 1, then one of these methyl branches goes on carbon 2, and the other one goes on carbon 2. This is 2,2-dimethylpropanoic acid. In this case, I've drawn the skeleton. To add hydrogens, in this first example, I will do the condensed version, adding just enough hydrogens to each carbon to make sure that the carbon has 4 bonds. So you will count the existing bonds already. The first carbon and the middle carbon already had 4 bonds and didn't require any extra hydrogens. Let's look at the bottom example, 1,1,2 pentane triol. I see the word all and know that I have an alcohol group. Pentane tells me it's based on a 5-carbon chain. The parent chain is 5 carbons, 1, 2, 3, 4, 5. I have 3 hydroxide groups, tri-all. Tri meaning 3, all meaning hydroxide groups. Where do I put them? I will put them on carbons 1, 1, and 2. Now you can call carbon 1 the left or the right. It doesn't matter so long as once you've decided you stick with it. So I'm going to put one of my functional groups on this one. I'll call him carbon 1, another one on carbon 1, and then another one on carbon 2. Up, down, sideways, doesn't matter, remembering that each carbon can only have 4 bonds. Finally, I check for branches. There are none, and I can add hydrogens as needed. Hydrogens are only added to carbons. The first carbon has 3 bonds already and requires 1 more. Same with the second, has 3 existing bonds, requires 1 more. The third carbon needs 2 more hydrogens to allow for 4 bonds, as does the fourth, and our final carbon has 1 other bond already and will require a total of 3 hydrogens to maintain 4 bonds. There's lots of practice for you with naming and drawing alcohols in your workbook on pages 43 to 45, and carboxylic acids can be found in your workbook on pages 46 and 47. In our next lesson, we'll look at what happens when acids and alcohols hook up together to form another derivative called esters.